Hello, ladies and gentlemen, and welcome to today's web seminar with the topic Power Loss and Efficiency in the FVA Workbench. My name is Dennis Tasi, and I'm working for the FVA GmbH as software developer. To my background, I'm a mechanical engineer, and before I joined into the FVA GmbH, I worked around 10 years for the automobile industry as a gear designer and analyst for manual transmissions. I planned for today's web seminar to show you the following steps. First, I will shortly introduce the FVA and the FVA Workbench. Then we will see the theory of the power loss calculation approaches. Most time we will spend today with the live demo directly in the FVA Workbench. I will show you on our virtual FVA gearbox, the operating concept, how to do such a power loss and efficiency calculation, which options are available. Also, I will shortly show you our scripting capabilities, because it's a very powerful tool to do parameter studies, optimizations, or for this case, e.g. an efficiency map. And at the end, I will summarize this web seminar. We start with the introduction. The FVA is a research association for drive technology, which is a network between the industry and the top universities. It promotes the competitiveness of small and mid-sized companies. Also, it supports the applied research activities at the universities and serves as a communication and training platform for its over 300 members. The FVA GmbH is a joint venture between the FVA and the VDMA, and the main mission of the FVA GmbH is to transfer the research knowledge of the around 200 projects per year to the member companies and to make the know-how usable at the daily business. This research and innovation network exists and is successful since over 50 years. To make the newest research know-how usable, the FVA GmbH has developed the FVA-Workbench as a leading software for designing and analyzing gearboxes. Also, we offer services all around the gearbox and trainings for software and for drive technologies generally. And we have a lot of conferences like Emotive and Bearing World. On 15th of November, that means next Monday, we will release a new FVA Workbench version 7. And what is the FVA Workbench in detail? It is a comprehensive tool to design and analyzing gearboxes. And it contains a variety of components such as shafts and cylindrical bearings, cylindrical gears, bevel gears, plane bearings, any types of shaft-hub connections, and so on. If you'd like to know more details, you will find the description of the modules on our website in the section Software and Features. Also on this website, in the section Software and Tutorials, you will find recordings of past web seminars. Now we come to the basics of the power loss analysis and the efficiency at the gearbox. At the gearbox design process, typically we have conflict of aims. Highest priority is mostly the load capacity of the gearbox, then followed by the noise behavior. And the efficiency most time is analyzed at the end when the gearbox design is nearly fixed and you can change a lot of factors. Today, with the more and more important requirements for the CO2 emission reduction, the efficiency of a design is moved in the focus. So the today's scope for this web seminar will be the efficiency analysis in the FVA Workbench. The total power loss of a gearbox, the total power losses of a gearbox are the sum of the losses at the gears, the roller bearings, and the sealings. At the gears and bearings, we differ between the load-dependent, torque-dependent, and the load-independent, only speed-dependent losses. For other gearbox designs, although the special approaches for sliding bearings, for splashing losses of the planetary carriers, or other losses like the power for the pumps, for the oil pumps, have to be taken into account. One of the most important power losses are the load-dependent power losses of the gears. They will be calculated similar to the Coulomb friction. We have the tooth loss factor, which includes the geometry of the gear mesh, like a contact ratio, helix angle, gear ratio, and the position of the pitch point on the line of action. It can be determined by an approach according to Ohlendorf, the basic approach, and there's with an extension according to Wimmer. Or another more detailed approach is a local geometrical tooth loss factor. This includes also the micro modifications and the detailed contact under load. So this approach is taking also the system deformations into account and the resulting gear mesh misalignments. For bevel and hypoid gears, there's an approach available according to Wech. To calculate the friction losses, we need additionally the mean friction coefficient, which takes into account the sliding roughness and so on. We can calculate it according to Schlenk, this is the simplest approach, or a little bit more detailed according to tutotial. But here you need the corresponding measurements from special tests for your lubricant. For bevels and hypoids, there we have an approach according to Wech. For the load-independent power losses of the gears, the type of lubrication is important. We have, on one side, we have the immersion lubrication. It consists of squeezing and splashing losses and can be calculated according to Mautz or Walter. Squeezing losses are resulting of too much oil in the gear mesh, which will be squeezed out during the gear meshing. Splashing losses are resulting of the teeth of the gears which submerging into the lubricant. We have now the option to visualize the global oil level in the 3D graphic. The second type of lubrication is injection lubrication. Here we have squeezing losses too, and additionally impulse and ventilation losses. No splashing losses. The squeezing losses will be automatically calculated according to Mautz or Butch. This is depending on the pitch point velocity. And the same automatization is done for the impulse losses, which will be calculated according to Ayura or Butch. Impulse losses are resulting of the injection jet, which is aimed on the gears, which can decelerate the rotation depending on the position and direction of the jet. The ventilation losses are resulting of the rotation of the teeth inside of this oil-air mixture and will be calculated according to Maurer. For the roller bearings, we have implemented the 3 bearing catalogs from SKF, from Ina Scheffler, and from Timken. Each catalog describes its own power loss calculation approach, and depending on which bearing is specified, the corresponding catalog method will be used for the power losses automatically. But as an alternative, it is possible to choose the ISO 14179 Part 2 approach. And this is similar to the old SKF method of 1994. The most detailed approach is the actual SKF approach, which is shown here shortly. We have the sum of the torque losses, and it consists of the rolling friction, sliding friction, the contact of the sealings, sealing friction, and all what is lubricant related, the drag torque. At the sealings, the power losses can be calculated according to 3 different methods. The first approach is the ISO 14179 Part 1. This is a US approach, which takes into account the rubber material of the sealing. Means if Vuitton or Buna N is used, this you have to specify on your sealings. The second approach is according to the ISO 14179 Part 2. This is a German approach, which only considers the contact diameter and the relative rotation speed between shaft and sealing. And we have an additional approach according to Linke implemented. This approach is an extended one, which also considers the oil temperature and the resulting viscosity of the oil. We have also some other components with power losses in the FVA-Workbench, which I will not show today in detail. But shortly here, at the planetary carriers, for example, We can calculate the splash losses according to Kettler. Here there's a difference if we have one or two-sided planetary carrier. At the one-sided planetary carrier, we are analyzing the planets which are splashing into the oil because of the rotating of the planetary carrier. And at the two-sided planetary carrier, we have the closed package with the planets inside. So we're only analyzing the outer package geometry and not the single planets for the splashing. The splashing of the rotating of the planets itself will be analyzed separately at this gear mesh. For plane bearings, we have the calculation kernels composed radial and axial implemented of the ETH-R of the Technical University of Clausthal. This was just a short overview which methods are available, and if you like to see more, this formulas, such as background, and some detailed descriptions, then you can find the descriptions online in our FVA-Workbench knowledge base under this link you see here below, or directly over the knowledge base button in the Workbench. Now we come to the practical part of the web seminar. The main part is now the live demonstration inside of the FVA-Workbench. Therefore, I will switch to the Workbench. You can see here, that's the first page. We will start with example models, because example models, they are included in the FVA-Workbench. That's a good start to try out new capabilities, to show what is possible, how to specify, and which data you will get as a result. I decided for this web seminar today to use the FVA virtual gear unit to show you the power losses. This will read the mesh file. And then you can see here the 3D model of the gearbox. This is now inside the housing. You cannot see much. We will select the FE part, the housing, and right click and we'll hide the component. And then you can see the inner parts. Here of this gearbox, we have one stage, one bevel stage here. We also have the next stage is a cylindrical stage with helical gears. And the last one is a helical stage with spur gears. We have input shaft with a ceiling, output shaft with a ceiling, and between all the shafts are supported with bearings from SKF. We have now here in the 3D plot the opportunity to select or to add, to show the oil level. We will start here. You can see now the predefined oil level. This is below all these axes and is parallel to the axis shafts. And here you can see a lot of the bearings and the gears are not submerged, not submerging or not have no contact to the lubricant level. We will change this later on a little bit. The first thing I typically do, I select the gear unit, and then I deactivate all predefined calculations. I go down and I activate the power losses only. And then you can see here a sheet with power losses. This is a power loss sheet for the global definition for the gear unit. You can see here general specifications for this power loss analysis. You can here specify if you have an oil sump in your gearbox, yes or no. And here the next one is very important. You have a reference shaft for the oil level. This is a global oil level. You can specify this is minus, it's below the shaft center, or it's plus, then it's above. Now at the moment we have minus 100, so it's below to the center of the shaft. We will do this in this run for 0, so all parts are half submerged in oil. So we can see for each component also load independent power losses. We have the oil volume in the casing and the general volume casing. And then we have a great section here with all power losses you can activate or deactivate. You can consider or not. We have the losses of the cylindrical and bevel stages. There we can activate or deactivate. The load-dependent meshing losses, load-independent meshing losses, and if we have injection lubrication, we can also consider the ventilation losses or deactivate it separately. For the cylindrical stages, we have a global definition of the tooth loss factor. We have here this, according to Ohlendorf, the extension by Wimmer. But for today, we will show the local calculation based on load distribution. This is the three-dimensional tooth loss factor, the local geometrical tooth loss factor. Here we can activate or deactivate the power losses of the bearings, and the next the power losses of the sealings. For sealings, it's the same like for the tooth, like it's a tooth loss factor. Here we can decide globally for all sealings the type of calculation. So here we can show you more. We will select US approach. Then we can select now additionally also the rubber material. The last section here I will not show you in detail today. It's for the thermal heat management. You can also specify the heat dissipation of the casing, the foundation, the flanges, or if you have an external cooler with special geometry, and so you can specify all your heat dissipation, and your heat source is the power losses, so you can calculate your temperature distribution. We will start now with the specification of the single components. So we select here the casing, and here we have a lot of roller bearings in our transmission. All of these bearings are SKF bearings, catalog bearings, so I will not show all of this in detail, only at one. You can see here is a bearing power loss sheet, and you can see you cannot select a lot because it's a catalog bearing, and all specification, all the data is covered by the catalog. So here you have only the choice of the lubrication type. If this is oil injection lubrication, it's oil air lubrication, oil bus lubrication, or if you have no oil design, you have grease. I have now for all these bearings specified it's oil bus lubrication. You can see in the oil level that all are submerged, so we will get an effect on this oil. The method of the bearing power loss calculation is default catalog method, means for this case it's according to SKF. An alternative would be here according to ISO 14179, and then here you have to specify the both factors manually here for the load independent losses or for the load dependent losses. You can see here it's support, the attribute help, which factor depending on the type of bearing you have to choose. But for our first run, we will use the catalog method. This is very important. You can see we have now a global oil level specified. So all immersion depths of each gear, each bearing is calculated automatically. But if you want, or if this shafts are not parallelly to the oil level, you have here a slope maybe, then you have to specify for each component, for bearing and gear, your immersion depths individually. Therefore, you can activate this checkbox and can type in here your immersion depths, how deep it is submerged. Another part here in the housing are the sealings. You can see not much because it's a simple approach. You have here the calculation internally, or you can also specify user input, the torque loss manually. And here, because it's in the US approach is activated, so you have to choose here the rubber material, Vuitton or Buna N. Next will be the bevel stage. Here we have also again the power loss sheet. And here we have now the specification of the friction coefficient. This we can specify individually on each gear mesh. So if you have some measurements available or something, you can here specify it by user input, or for bevel stages, a typical approach is only available is a approach according to WEG. With the lubricant factor, it's considering the type of lubricant. Here you can specify if this is a synthetic lubricant, minor traction fluid or something else. If here the support of this table, you can change this lubricant factor. And now all below, you can see here, it's just identically between a bevel or hybrid gear or a cylindrical stage. This is a part of the load-independent power losses. You have here the first point is the choice of immersion lubrication or injection lubrication. And if you leave letters here on immersion, you have next point the specification according to Mautz or according to Walter. So if you're having according to Mautz, you have this setup to specify. If you have according to Walter, then you have a little bit different setup to specify, like equivalent tutorial length and so on. We let it according to Mautz. And then we have for the splash lubrication, we have here, you can specify the immersion depths. You can manually specify the height of pitch point over the deepest immersion. So there's this size here, but if you will let it free for a cylindrical gear maybe, then it will be determined automatically. Next point will be the stage position to the oil. This is here automatically. This is important for the load-independent power losses according to Mautz. And here this is automatically determining if the gears are vertically to the oil level or horizontal orientation, and if the rotation is feeding the gear mesh directly from the lubricant level or indirectly over the walls of the housing. And here, with these factors here, you can specify for the splashing losses the distance to the walls. Means if you have smaller distance, then you will get more interaction, more splashing losses. Next point will be a cylindrical stage. We can also choose here the power losses. And now we have here the friction coefficient according to Schlenk, tutotial, or user input. What does it mean? This Schlenk is a typical approach, a default approach. If you have more data, you can use an approach according to tutotial. What does it mean? It's related to the type of lubricant. If you will choose here the lubricant in the model tree, you have the chance here to specify the friction coefficient according to Schlenk. You can specify it manually depending on your lubricant, or you can do it automatically depending on the lubricant type. Then it will be determined automatically. If you want to analyze the friction coefficient according to tutotial, then you have to specify, depending on the test and the measurements, these 11 factors here to specify the behavior of your lubricant more in detail. For our first run, we will let this according to Schlenk. We'll say it's immersion lubrication, and the rest is default and identically input data or set up like it's bevel stages. Now everything is defined. You can see the basic setup for immersion lubrication with a level in the middle of all components, and then we can run the system calculation. You can see here our message board. So you can see below at the top and at the bottom, you can see info messages, and above a lot of warnings. These are mainly warnings because some sizes are out of the validity range, because all these approaches for the load independent power losses are validated for a couple of gear designs and gear mesh designs. And so strictly it's in this range is valid. And if your gear design is completely out of range, you have to take care on, and you have to be carefully with the rating. Now all data of the input and all of this power loss calculation run is stored in this model snapshot here. And now we have to choose to select which data we like to have in our report. Therefore, we have report templates available. This is a type of filter. And we have now here in the overview report, a compact report available for power losses. Then double click on the model snapshot. And now you can see here our predefined report template. We have here's our model tree. Here's a hierarchical tree. You can see the gear unit. Here's, for example, is the power flow, input and output torque, and power and speed. We have, and this is an overview table of all power losses in our gearbox. You have the efficiency of the gearbox and the total power loss. And below we have the total power loss of all the gears. Then the load-dependent power losses of all the gears, the load-independent power loss of the gears, and the same for the bearings, and at the end here for the sealing. And to get a better feeling of these numbers, we have this graphic here. You can see the both main parts for the power loss are typically at such applications, the gearing losses load-dependent and the bearing losses load-dependent. But this depends on your gearbox and your specification for speed and torque. Then we have the operating data. That's oil-related data mainly. You have operating temperature of 80 degrees of the oil temperature, and then all lubricant data for 80 degrees for kinematic, dynamic viscosity, density, and so on. Then for each stage, we have here an overview for each cyclical stage, overview of the main geometry, the operating data, torque input, output, and speed, what is going above the stage. And then we have two sections. We have the section load-dependent losses and load-independent losses. For the load-dependent losses, we have here the overall power losses, and then we have the friction method for the mean friction coefficient, and for the tooth loss factor, we have here the specification and all data which is necessary to rate this data. For the load-independent losses, we have the overview of the power losses, load-independent, and the immersion depth, for example, here, which approach is available, which approach was selected, and then we have a section for splash losses and for squeezing losses. For our gearbox here, you can see our splash loss factor is 0. We can see in our model at the end. Next point will be bevel stage. Here is also the same. You have a load-dependent gear losses, a load-independent gear losses, then an overview of the total gear losses. And a very detailed report also. It's about the roller bearings. Here we have the SKF catalog method, the oil bars lubrication type, and then you can see here the overview of the total power losses, the load-dependent and load-independent losses. The load-independent and the load-dependent losses. And then the different sections for rolling friction, sliding friction, direct losses, or the sealing losses. For the sealing, it's a little bit shorter. You have only the power losses and the torque loss. You can see the approach for the calculations, the rubber material, and then the diameter and the related shaft speed. This is a typical report or compact report for power losses. Now we have seen this squeezing losses are 0. Why are these losses are 0? Because if you run here the simulation, maybe a little bit slower. you can see that the rotation direction, the mesh is going inside of the lubricant, and the lubricant will be feed into the gear mesh indirectly over the balls of the housing and over the splash here inside of the meshing, or here or here. If you would reverse the rotation direction, if you revert it, then you will get also squeezing losses. Now we have run here a simulation run for this gearbox for immersion lubrication, and then it's a typical question, how to improve this power losses, reduce the power losses, and improve the efficiency. And one typical way is at the end is a question if low viscosity oils are beneficial. Therefore, we will change the lubricant. First, I will rename this snapshot here to the lubricant 320 reference. Then we will add here in the local data pool lubricant. Right click, add a record on screen, and now we will add here ISO with 32. You can see here now it's added here to the local data pool. We will go to the gear unit, then section operating data, and here we can specify the lubricant to the other one with the low viscosity, same temperature, everything is the same. Then when you run again this power loss calculation, we rename this. Then you can select this as reference, right click, set as reference, then select the second run with the low viscosity oil, right click, and compare with reference. Then you will get a report with A to B comparison. You can see on the right column this normal lubricant and the low viscosity oil on the left side. And then you can see what does the effect on the efficiency. That it is slightly improved, or what does it mean for the losses? The losses are reduced also. So you can analyze the effect of the different lubricants, where they come from, what does it mean here, for example, for the load-dependent losses or the load-independent losses, where are the factors which are influenced by the lubricant. We will set this back to the other lubricant. And what's now also possible to reduce the oil level in your transmission. Also a typical idea at the end of the gearbox design. You can select the power losses and say it's minus 100 millimeters. Then the lubricant level is dropping down. You have less components splashing in the oil. Run again this calculation. Then we will rename it again. Right click, rename 320 low oil level. And then right click, compare with reference. You can see here that's also significant better efficiency, and for example, a significant lower power losses, because all the drag losses of the bearings and a couple of losses of the gears are reduced. So here you have to find the good trade-off of your lubrication. Now we will change a little bit our specification. We will specify on the bevel stage, on the cylindrical stage, another type of lubrication. We will select the bevel stage here and say we are choosing injection lubrication. Therefore, we have to specify the nozzle diameter, for example, 1 millimeter, Then one of the other Bose values here, we say injection speed 3 meters per second. Then the oil volume flow is automatically calculated. And then very important is the positioning and the direction of the injection, because this information is not available without a specification. You have the different variations here. You can specify down in meshing direction or up in meshing direction, or you can specify it against meshing direction. So for this run, I will try down against meshing direction. Then the spray is aimed against the rotating direction. You can see here a ventilation for the ventilation losses, similar to the splashing. You have here also water distances you can consider. And then we will do the same for the both other stages. We will specify here injection lubrication. For the cylindrical stage, we will say nozzle diameter of 1 and injection flow rate of 3, and the direction of the injection from the bottom to up, down against meshing direction. And the same for the nozzle stage. And down against meshing direction. And now run again. We name it injection. And then we will compare it with immersion lubrication. Now you can see here some differences. For example, you can see for injection lubrication, the total power loss is significantly lower than for immersion lubrication, because here you have more splashing losses. It's more related, leading to more power losses. But here you have to take care on, because here with injection lubrication, you have lower power losses, but therefore you need for the injection also power for the pump, which is not included here in this calculation. If we want to take a look on the cylindrical stage here, you can see a little bit lower. You can see some differences. You can see splashing losses. There are no splashing losses for injection lubrication, but we have squeezing losses. Now in this case, both are 0 because of the rotation direction. And we have impulse losses and ventilation losses, very small losses. So this is the basic I want to show on this example. And you have seen more or less all what you can specify here for your setup. Next point will be here. I will show you slightly some capabilities for scripting, especially for this type of transmission here. I therefore will load a predefined gearbox. Here I have added a script to do a parameter study for torque and speed. Because for efficiency, it's always important to get such type of efficiency map, or to get a parameter study to get a feeling about what does it mean, torque and speed, where is the highest efficiency, the best torque transfer, and which component is the most critical for the power loss. For scripting, we have here another Windows scripting, an extras in scripting. And you can see here it's a script. It's not so easy to see. Maybe I will shift to Notepad. Here's this text highlighting, maybe a little bit easier to understand. It's just a short overview of scripting. It's simpler than it looks like at first view. Here we have to specify the model path, and here is one point we have to specify an Excel sheet as an input sheet and specify that the input will also used as a template for the output. Then here's a short check. If the output Excel file is open, then we will read some data from an Excel sheet, specify, initialize all the parameters of all the losses, the power loss, efficiency, and so on. Then we read the data for our study. We want to vary the speed and the torque, and therefore we have then now two loops, one external loop for the speed and one internal loop for the torque, and then we will run here, do a run for each torque and speed combination and write down all the outputs of the gearbox. And right at the end, we'll write this data in the workbook in the Excel sheet. We have one input Excel sheet here. This is what we are using for as also as an output template. Here we will read out the gear unit, which will be used for the study. Then the script is reading the load ID, which where the torque will vary. Then the speed ID for the shaft, where we will change the speed direction. And here we have specified 10 torque levels and 10 speed levels, and we'll use this template here also as an output. This you can store here in the script inside of the model, and then you can save or store. You can also run here this model, and now you would run here automatically 100 different combinations for speed and torque. And you will get for each output, you will get such as a snapshot, but this you can also deactivate. And you can see here it's just a monitor output for which speed and torque range actually we are performing. This calculation run here, automatic run, will take around about 5 minutes. It's a little bit too much for today, so I'll cancel this run and I will show you the results. We will switch back, and this is now the result of the Excel sheet. You can see here the efficiency, torque and speed dependent, and the total power loss. You can see the total power loss with larger torque and with higher speeds. You will get at the end the biggest losses, but the biggest losses are not at all the lowest efficiency. The best efficiency you have for this gearbox for low speeds and high torques, and the worst efficiency for high speeds and low torques, because the speed relationships has a higher effect. You can see here these are the total load dependent gear losses. On the left I have the load dependent gear losses, on the right the load independent gear losses, and you can see at the load dependent there we have also an effect on the speed. So with increasing speed and increasing torque we will get higher losses. And for the load independent losses we have only an effect in speed direction, not in torque direction. And you can see here on this highlighting of the colors that for this setup we will get the highest losses at the load depending losses on the bearings. And load independent bearings are not so small, but significantly smaller than the load dependent losses. And the sealing losses you can see nearly nothing because they are very small. So you get the chance to do such a big study within a few minutes if you have the scripting available and you take your time to build up some easy scripts. So it's a very powerful part to optimize also your gear design related to efficiency and so on. So it's a very beneficial option. maybe I can show you another part. No, I will switch back to the presentation. We will come to the end, and I will summarize this web seminar from today. We have seen the theoretical background of the power loss analysis. In the table on the right side, you can see all implemented methods by name. And if you need more information about this approaches, you can find this in our online knowledge base. The main part of today's web seminar was a live demonstration directly in the FVA-Workbench. Here we have seen the operating concept for the power loss analysis, how to specify the components, and how the report template looks like. Also, some parameter studies were shown on shortly the capabilities of scripting to get an efficiency and power loss map. You can see here below. And I think with this user-friendly operating concept in the FVA-Workbench, the power loss calculation can be performed directly at the beginning of the design process and can be considered at the beginning and not only at the end if everything is finally designed. Don't miss our next 3 web seminars. We have 4 additional web seminars in pipeline. You can see here tomorrow with interface to AVL site, an example for an E-axle. And next week we have local load capacity of the linear stages in the FVA-Workbench. They will be presented. And we have also the wheel body design in the FVA-Workbench. Means this is a flexible wheel boarding which considers such bores and special symmetric and asymmetric designs in the wheel body. And we have also one web seminar available about plastic gears. This is a local contact analysis with non-linear non-material plastic materials. Also, thank you for your participation, and now I like to answer your questions. I have here a question: is there a possibility to receive the presentation? No, it's not planned to share this presentation, but in a couple of days you will find this presentation online on our website, and this is a YouTube plugin, so you can also find us on YouTube. Let's see more. If the gearbox has separate oil sumps for different gear stages, can we enter the oil levels and volumes separately? The oil levels is not a problem. You can specify for the oil level for each component separately. For the oil volumes, this at the moment is not planned. So at the end, this calculation is done for the overall oil volume. So if you have different sums and would completely analyze it separately, I think you have to specify 2 models. What is a 3D data interface? What do you mean with a 3D data interface? Maybe we can specify this question later on. Can I import SolidWorks part data? Yes, sure. You can import this data. and then you can mesh directly your parts and your components in the FVA-Workbench, if you like. But we have also others available like iGES and STEP and Inventor and ProE and CATIA. But I think SolidWorks should also be part. Yeah, as you can see here, these are our, at the moment, our available 3D models or CAD interfaces. So I cannot see more questions. So thanks a lot for your participation. And if you have some questions later on, you can also keep in contact with us, and we are pleased to answer your questions. And if you don't want to miss some web seminars or some information from our side, you can subscribe on our to our newsletter, or you can follow us at LinkedIn or Twitter. So thanks a lot for your participation, and wish you a nice day.